Okay, thank you very much, Weera. I'm just going to slowly start to make sure everybody can hear me and see my slides. Someone will tell me if it's not possible. But first of all, I'd like to welcome everybody who's spent some time to attend this webinar today. It's the fifth in the MRP webinar series. And before I start, I'd like to thank very much my colleagues at Pete Multibagana Rekatama Patria who do all the hard work to create these webinars. I simply arrive here on the day and present my material, but a huge amount of work is done behind the scenes. And I, as usual, would like to thank them and congratulate them very much on a very professional job. The topic today is a bit different to the previous ones, looking specifically at the CPT. And I have a lot of material as usual, so I need to move quite quickly. I think this is going to take me about 1 hour to present. So I'm going to put a little stopwatch on there. And then we'll have time for Q&A. If you have any questions, then hopefully I can deal with that. So it's the fifth in this series of webinars on geotechnical engineering, looking at the CPT. We've already been through that. And although it mentions the Holocene marine clays of Southeast Asia as the main subject of the testing, of course, the material would be applicable to almost any soft or firm clay deposit, even maybe slightly stiffer, but principally in the soft and firm clay region. In fact, following this, there will be a sixth webinar, which is associated with this one, and that's going to be specifically about the pre-consolidation pressure of these clays. So that'll be our July webinar. Just to let you know that the content of this is mainly based on a paper I presented at Soft Soils 2014 in Bandung, which I'll come back to briefly in a second. And I have extended it somewhat to cover other elements of data, important features of testing and so forth. And I also presented this at a HATI workshop organized by the company GeoMill back in 2016. So it's similar, but with some changes. This is a summary of the MRP webinar series to date. The one in bold there, June 2021 is today. And you can see how the one in July will be this special one dedicated to the pre-consolidation pressure. And then beyond that, a few more with the intention of completing these webinars in November. Just a few images, CPTs in soft soils. So that wonderful looking truck there is what's called a ballasted CPT truck, where it weighs about 22 tons. So it has all of its own reaction built into it. This picture is taken in the early 80s, and I'm in that picture, and there are no prizes for trying to guess who I am amongst the four people. We'll talk a bit more about these sorts of CPT machines in a minute, so we'll get back to those. I'll also mention an associated test, which we often do in conjunction with CPT, which is the vein test, a very important and useful test and worth talking about briefly. Quite a lot of attention will be paid to the piezo cone, which looks like this. And also, I want to talk a little bit about presentation of data and interpretation of data and some of the important issues to do with that. So who is this intended for, this webinar? Because we're going to look at the CPT in some detail, the equipment, the operation and interpretation. And I realized that in fact, many engineers who perhaps make use of CPT data don't get a chance for what I call hands-on experience in these techniques. It's not so easy to do that. So hopefully this will be very useful for any engineers who are either writing site investigation specifications or interpreting reports which include CPT data. Throughout this presentation, as usual in these webinars, there will be little blue boxes appearing which provide some additional comments and information, and some of them pose a few questions as well. So this is aimed mainly at civil engineers who have some involvement in ground engineering and site investigation in particular. and hopefully it will be of interest to more experienced geotechnical engineers. But in this case, the main target is the site investigation of soft soils. But I just want to come back to this hands-on comment I made earlier on, because I've been rather lucky in my career to have two spells where I've worked in this field, which I think is the reason why I feel I'm qualified to talk to you about this today, and basically to share my experience of being involved in hands-on organization and actually carrying out this kind of testing. The first period was with the Del Sol Mechanics Laboratory. I worked there for 4 years, and from 83 to 85, I was in Singapore, where we were operating this magnificent vehicle, doing CPTs all over Singapore to do with the very early stages of the MRT. And in that time, I was using mechanical CPT, also electric vein testing, pressure meter, and also the 66 millimeter Delft continuous sample, and you'll see one of those in a minute. And then the second period where I had a chance to work on this in great detail was in Malaysia, where I spent 2 years working at the Central Soils Laboratory for the North-South Expressway project there. And there we were carrying out pizza cone testing, vein testing, Marchetti dilatometer, a lot of piston sampling, and of course, laboratory testing. And actually in that picture there, there's a rather distinguished, taller gentleman towards the right. I'm sure many of you won't recognize him, some of you may, but that's Professor Peter Roth, sadly passed away quite a few years ago. But he was one of these very gifted geotechnical engineers, and his contributions to this subject are very big. A few comments about reference material that you might find helpful. And I've got quite a few here because, in fact, there's a huge amount of published information about CPT and cone penetration testing, pizza cone, and so on. The left-hand document there is actually an FHWA guideline written by Schmertmann. The reason I mentioned that one, apart from the fact I got it on my bookshelf, but also it is principally aimed at the mechanical CPT, or the sondier, as we tend to call it here in Indonesia after its Dutch name. The other book, slightly more recent, by Lun et al., is a very comprehensive document, and one worth getting if you're working a lot in CPT. I also mention here 2 UK publications, a Syria report and also an ICE conference, which I attended and I presented at. That's the right-hand document. But I show this partly to make the point that although the origins of the CPT are essentially Dutch and from the Netherlands, it's become a technique used everywhere in the world. I think most people appreciate that this is a technique from which you can get a huge amount of data. It's a very excellent test in many soil types apart from the soft clays. So just a reference to some of that kind of background. And some more recent publications here. Left hand is, you can download that from the internet, and I recommend you do so. It's published, or it's written by Peter Robertson, who's a well-known expert in this field, and worth getting hold of that document. And then the other document is one of the events is organized by UNPA, Universitas Parahyangan in Bandung, and that particular one was Soft Soils 2014. Now, I'd like to make a mention of another person here, Professor Paulus Raharjo, because he organizes many of these events. They're normally every year, although currently it's a bit more difficult with the COVID situation, but quite a few of these are dedicated to soft soils. And also in particular, we have noise coming through. Don't know who that is. Someone not muted. Never mind. Okay, but Paulus has made a massive contribution to soft soil testing, in particular CPT. He's passionate about it, as indeed I am too. And I first attended an event in Bali about the CPT, where he also managed to attract Peter Robertson to come along. So that was a really good event a long time ago. I've also published a few papers myself on the topic. Just to show a couple of them here, on the left is actually published in ISOPT. That was the International Symposium on Penetration Testing, the first one in 1988, which was held in Orlando, Florida. So that was quite a nice trip to go over there and attend that event. sadly a bit more difficult at the moment. And the other one was from Soft Soils 2014. In fact, the paper on the right contains a lot of the detail that I'm presenting today, and I'm quite sure if you want to get a copy of that, it can be arranged. So let's talk about, well, just summarize the contents today. We're going to talk briefly about the main subject of this testing, the Holocene marine clay, and then an introduction to CPT and some of the issues, also to the vein test. We'll then look in a bit more detail at the mechanical CPT, often called Sondier, as I mentioned. Then the piezo cone test, sometimes called CPT-U. U is for pore pressure. We look at correlations with design parameters, just restricted, mainly looking at undrained shear strength. Then we'll look briefly at a case study to do with embankment stability. And finally, a few words about planning site investigations using the CPT in soft soils and some of the benefits you can obtain from doing that. There will be a quiz, as usual, at the end of this webinar, and it's going to be related to some of the material presented, and there will be prizes for the winners. So, an introduction to the Holocene marine clay. This is a map that you can find in the Indonesian GeoGuide, and the black areas are referred to here as quaternary deposits, and those will include the Holocene marine clays. They're generally around the coastal areas, and they are extensive. So they are important deposits when it comes to the construction and design of infrastructure in many parts of Indonesia and also many other Southeast Asian countries. You could find similar maps for Malaysia, Thailand, Philippines, China, Vietnam. They will all have similar maps where you can see the extent of these deposits. Now, this particular picture, I kind of show it quite often to people, but I still find it's a very good starting point. It's a 26-meter long sample taken with the Delft sampler of the marine clay in Singapore, and the bottom part of it is what we call the lower marine clay, which is not really the main subject today. That's a slightly older deposit, maybe 100,000 years old, something like that. The top of it is actually an old land surface, and you can see the brownish material roughly halfway across there. That's probably old topsoil. And then the sea rose again because the ice melted following the last glaciation. And then we had a period of deposition where we see the upper marine clay, which is the Holocene deposit. Holocene means recent life. It's a geological term, and it basically covers about the last 10,000 years or so. Very recent deposits. So the upper marine clay is young. It's maybe between 4,000 to 8,000 years old when you encounter it on land. And I will come to that briefly again in the next couple of slides. So hopefully this gives you a bit of a calibration. I'm not going to talk in great detail about the contents of that because I've done so before in a previous webinar. This little diagram remains important when you think about this because it's a graph of sea level. The horizontal axis is thousands of years ago. We're at zero, of course, and the vertical axis is the mean sea level relative to today, and zero, of course, is where we are. And you can see how the sea level went down, 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 and then came up again. And from the point of view of the marine clays, their depositional periods are very short and very obvious. And the yellowish line there is when the lower marine clay would have been deposited. But the upper marine clay, the Holocene one, is the red line. It's clearly very young. I said around about 4,000 to 8,000 years old where you encounter it on land today. And that's an important point. So here is a marine clay site in Malaysia. It's a Holocene marine clay. You can see that because the buffalo is covered in it. And probably at that site, which is currently maybe 1 to 2 meters above sea level, deposition must have ceased about 3,000 to 4,000 years ago. So on a site like this, the soils will be lightly over-consolidated and they will not be under-consolidated. It's important to make that point because under consolidation, these are deposits where consolidation is still going on. Now, you would find that in young deposits. This is an aerial picture of the Mahakam Delta where we have deposition going on at the moment. So these are Holocene deposits, fine deposits, and almost certainly they could be underconsolidated. And this rather well-known graph is often being used to demonstrate the point about underconsolidation. And what you see there is rate of sedimentation on the horizontal axis in millimeters per year. That's the material being deposited. And the vertical axis is the average degree of consolidation. And you can see that it only becomes 100 when you get very, very slow rates of sedimentation. And you've got the different soil types that might be encountered or involved in the deposition. This graph dates back to 1968, published by Morgenstern. And the typical deltaic clays of Southeast Asia are somewhere down inside the red band. And from the point of view of Indonesia and also Thailand, those are the typical ranges of rates of sedimentation. But the point is that you only get this partial consolidation where you have ongoing sedimentation. That's rather important to comprehend. So today I'm principally talking about the marine clays which are currently forming dry land and have therefore been there for at least 3,000 to 4,000 years. Now, what are the main problems? Well, I'm going to really be talking about the situation where we want to build fills, maybe road embankments, rail embankments, other kinds of fill for developing maybe real estate or housing estate. And when you place fills of marine clay, you're first of all going to be concerned about stability at the edges of your fill, where you might, for example, generate failures like this. And that's a short-term problem. And probably that's the main target of today's presentation. However, there's also another issue, of course, which is the settlement of these fills. And that's a longer term problem. And that's really more of the content of the next MRP, the 6th webinar, which will be next month. We'll be looking at settlement. Now, a few introductory words to the CPT itself. They have enormous benefits for site investigation in the marine clays. But this is a big question that you need to consider when you're reviewing data. Is the data suitable for deriving engineering properties, or is it only suitable for profiling? Profiling essentially means telling you the extent of the deposit. Very important questions. And that's really part of what I want to talk about. We're going to talk about the mechanical CPT and also the electric CPT, which will come second. And that'll include talk mainly about the pizza cone, sometimes called CPTU, as I mentioned earlier. The main parameters of interest are the undrained shear strength and the pre-consolidation pressure. In fact, we can derive many other properties from CPT results. And if you want to learn more about that, I suggest you get hold of that Peter Robertson guide. But we're going to concentrate mainly on those two in these webinars. One thing I like to make, and I think this is an important point, is that in soft clays, the CPT is an undrained test because it's done quickly. So it's really only suitable for determining undrained parameters. Please be aware of that. If you find yourself trying to interpret phi dashed in the marine clay from a CPT, I would be extremely cautious about any answer you might get. So there are two properties. Really today, it's undrained shear strength, and the next webinar more about the pre-consolidation pressure. Now, important point is we cannot measure these directly from the CPT. So we must use correlations and methods of interpretation to obtain this kind of information. Some of the basic requirements of the equipment. There are four main elements in the CPT equipment. We have a jacking device, which can be done in a number of ways. And then we also have some kind of reaction because you're going to push downwards. So you've got to have something to stop things going upwards. And then generally in Indonesia, that's going to be done with little screw anchors. Then, of course, you need to have some kind of measuring device, which is going to be up above ground level. And then the probe is down, being pushed into the soil. And there are two main types of probe or cone, as we mentioned already, mechanical or electric or pizza cone. And I'm going to talk about both of them. Another term that you'll quite often hear when people are talking about CPT is the capacity of the test. Now, when you hear that, then you need to ask yourself, what are they talking about? Is it the capacity of the jacking device or the reaction or the capability of the probe? So someone might talk about a 2-ton cone or a 5-ton cone. Well, that'll be to do with the limit of the load that can be applied to the cone itself. So if you're talking about that, please be aware of the background to that capacity value. Here's a picture of the probe itself, just in a simple way. This is well known, I think, but from the bottom upwards, we have the cone itself, which has a certain angle, and it's 10 square centimeters of projected area, and that fixes the diameter, of course. And then above it, we have what's called the friction sleeve, and that's arranged to have a length to give you 150 millimeters, square centimeters of area, and that's where we measure the local friction. Then for the piezo cone, we would also have the addition of an element that measures pore pressure, U, and it can be located in a number of different places on the cone, but the most common one is behind the cone itself. And then in equipment, certainly for the electric CPT or piezo cone, then we should also have sensors to measure inclination and temperature. We'll look at both of those a little bit. In fact, inclination right now and temperature a bit later on. So this inclination thing is important. If you get to a site and you pick up a single CPT sounding tube and put it over your knee and try and bend it, you can't. It feels enormously stiff. But when you screw 20 of them together, then they become quite flexible. So I just want to show you a piece of information which relates to this. And it was work I was doing a long time ago in the UK at a place called Selby in the north of England. And we were doing piezo cone tests, but in those days, this particular cone could only give you 2 channels. And I chose that we should measure cone resistance and water pressure. They seem to be the most important. So there's a typical result and you're going to see many profiles. So let's just quickly check out what we're looking at. We have depth going down the vertical axis in meters and the various parameters on the horizontal axes being plotted there. And you'll see lots and lots of these profiles as we go through this material. So we have the cone resistance, which in fact is showing some fill material over some sand. And then the water pressure shows a very nice hydrostatic pore pressure response once you go into the sand. You can see it's been calculated and checked and it works out very well. So that was going on nicely. And then we received, I was actually down at my head office in London receiving information, and we received another trace like this. This is test number 54. And it was weird because the pore pressure was going up as we expected, but then it went down again. And people were getting concerned about some kind of strange drainage feature buried deep in the soil, but it was nothing to do with that. If we put the 2 traces together, you see them like that. You can see how the blue one starts off in the water pressure plot, much the same as the other one. But what's going on here is that the blue one is actually deviating from vertical. And by the time it gets down to that point noted just there, the cone is actually traveling horizontally, and then it comes up again. So there's been a massive deviation in test 54. And what you can actually do from this, you'll also notice how the trace on the left is quite symmetrical about that point. Not surprisingly, because it's coming back up through the same soil. But what you can do from that information, you can plot a graph like this, which is simply showing the depth of the test versus a horizontal distance. And you can see how test 54 would have deviated off and starts to come up again. So the point about this is that obviously for electric CPTs and piezo cones, they should always have an inclinometer, also because it helps to protect against breakage. But for the mechanical CPT, we don't have that kind of device. So we cannot check deviation in the mechanical CPT. So what's really important is careful setting up, maybe removing any near surface obstructions, like maybe rocks and things that could cause the probe to deviate off in one direction or other. And also ensure that all the probes and sounding tubes are straight, because even if, say, the cone itself or some of the tubes at the beginning of the string are slightly bent, then it acts like a rudder, and the whole thing goes off and will deviate. You can't do anything about it. So those sorts of things can be checked very easily before you do a test. Another important point about CPT is its use in soft clay. So this graph here is showing you cone resistance on the horizontal axis, and it's a logarithmic scale going up to 100 megapascals, which is very high. And the vertical axis is mean effective stress, essentially depth. And I've put on two sets of information there. I put on sand against different relative densities from 15% up to 100%. In other words, very, very dense indeed. And you can see the sand goes up to extremely high cone resistance. But at the bottom of the graph, I've put the typical ranges for very soft, soft, firm, and stiff for clays. And the typical range of the Holocene marine clays, you can see there in the middle. Now, the issue here is that this range of QC is very big. In fact, along the bottom of the graph is the load on the cone in kilograms. So when you're doing testing in a mixed deposit of, say, soft soils and sands, your cone may have to measure 10 kilograms 1 minute, and a bit further down, 5,000 kilograms or 5 tons. So this is an issue. This is an issue, and this means that your equipment must be capable of doing this. And there are ways we can deal with this, which we'll talk about certainly for the mechanical CPT in a minute. With regards to the electric CPT, the quality of these instruments these days means that they can deal with that enormous range of load capacity very well. A few words about the vein borer, or the in situ vein test. This is a test I like very much, and the in situ device works in much the same way as the CPT, and in fact, often now you can get vein test equipment which is also combined together with CPT equipment. But this is a simple device called the Geonor vein borer. You have a frame which is again anchored with a jack, and the jack allows you to jack the various devices down into the ground until you reach a required test depth. And we often do this in conjunction with the CPT because it gives us a way of correlating. Having reached the required depth, you then need to clamp the outer tubes of the device. And having done that, you then push out the vein itself into the soft soil. And with the vein pushed out like that, you then apply the torque device on the top, you attach it, and you carry out the test. In the Geonor equipment, there are two vein sizes, a smaller one and a larger one, and the height to diameter ratio is generally taken as 2. So just looking at it in a bit more detail, there is a picture of a vein on the right-hand side. And after it's pushed into the soil, we normally wait 5 minutes, and then we apply a torque to the top at a particular rate of rotation, and until it fails, and then it's the peak strength. Having done that, we then turn the vein round a few times, wait another 5 minutes, and repeat the test. And that's what we call the remolded strength. So there's some nice pictures of the actual equipment close up. You can see there the two very clean looking veins. They haven't been used yet, the two sizes. And then on the right, you see there the torque head and the device where we can retract the vein into that device so it's protected during insertion. So one thing I like about the vein test is very simple equipment. It's very robust, and often people get very worried about the calibration of the torque head, but we calibrated ours several times and it never ever changed. It was a very dependable piece of equipment. So simple equipment, and from this you can get wonderful information. So here's a profile of the vein shear strength, SUV, on the horizontal axis against depth. And in fact, in this particular case, we were doing tests every half a meter. So there's lots of data. That's the upper marine clay, the intermediate layer, and then the lower marine clay. We have the two traces, peak and remolded, and then the graph in the middle of this slide is the sensitivity. But it took about a day to measure that information. It's really quick to get so much data of such useful and high quality. Really good test. One thing you need to be aware about the vein test is that from research done principally originally in Norway by a famous geotechnical engineer, Bjørn, he discovered that the test, especially for high plasticity clays, tended to over measure. You got a strength that was too high, and he developed this correction factor, which you should apply to the results when you apply them in your calculations. And I'm going to look at that a little bit later on when we examine an embankment case study. Here are the bits and pieces of equipment that we use for the mechanical CPT. We have what's called casing at the top, which we use to stiffen up the string of rods if we're testing through very thick marine clays. Then we have the outer tubes and the rods in the middle, a couple of cones of different types, and the load cell itself. Here are some different devices. We saw this picture earlier on, but in the distance you have a 20-ton rig, with two very big jacks. The nearest one is a 10-ton rig, and the one in the middle is a hand-operated 2-ton rig. And these all require anchors. The good thing is, if you're testing the marine clay, because it's so soft, you don't actually have to develop a very high push-down force. So it's difficult to anchor near the top of the marine clay, but normally you can get sufficient reaction okay. Now let's see how it operates. It's rather important to see this. So there is a picture of a mechanical CPT probe, which I have in my office. You can see there the friction sleeve and the cone itself. So let's replace it with a kind of a little diagram like this, and let's just see how the test works. Now, first thing to realize is that the friction sleeve is around about, the center point is around about 200 millimeters above the cone tip. And it works like this, the test. So at the moment, the device is telescopic, which means it compresses and it extends again. So at this stage, what we need to do, we need to push on the outside to compress the cone and push it down to, say, the next test level given by the horizontal line. And then having done that, there's a little switch. We switch over and we push on the inner rod, the thin one. And to begin with, we just push out the cone by itself, which is normally called reading number 1. And that gives us the cone resistance. We carry on pushing, and then what happens is the telescopic action also pulls out the friction sleeve. So we get reading number 2, which is cone resistance plus friction. This is very basic information. I'm sure anybody who's worked with this device is well aware of that. Having done that, we then push on the outside again to recompress the cone and get it down to the next test level. So well known, but a few things to be aware of. I've got all these issues or things to be aware of. Issue number 1 is to remember that there is a 200 millimeter approximate difference between the level of the middle of the friction sleeve and the cone. So when you are interpreting the data, and say you've got a reading R1 and R2 at a depth of X, you've got QC, which is at X, and you've got QC plus FS. Now to find the local friction, we subtract one from the other and we get FS, but that FS belongs 200 millimeters higher up. So you need to position it at the level 200 millimeters higher. And then to calculate the friction ratio, which is the ratio of that one to the cone resistance, then you need to use the QC value from the previous reading. It's my experience that this is often not done when I look at the plots of sondir or mechanical CPT carried out here in Indonesia. How do you know quickly? It's very simple. Here's a very nice plot of a mechanical CPT. We've got all the 3 main traces, the cone resistance in the middle, the local friction, which is normally plotted on the left, and it's in the other direction. So this is quite a nice way to do it. And then the friction ratio, which is the ratio of local friction to cone resistance as a percentage, is plotted over on the right. That's how we normally do it. You can see it in other ways, but this is a normal way. In this particular test, for some reason, the readings were every 250 millimeters. It doesn't really matter. But the point is, when you look at the bottom, you'll see that the cone resistance plot finishes slightly deeper than the other two. And it should always be that way. So whenever I see these plots, that's the first thing I look at. To be honest, in a marine clay, it wouldn't make too much difference if you got it wrong. But if you're in a deposit where the soil layers are changing rapidly, this could be quite significant. Issue number 2 is to remember that we measure the load at the top. That's where the load cell is. And then there's this great big string of inner rods, which are also applying load to the cone. So the actual load applied, QC and QC plus FS, include the effect of the inner rods, which applies more load than you measure with the load cell. However, counteracting that a little bit, we're not sure by how much. You may have some friction between the inner rods and the outer tube, or you may have some curvature. That would also increase the friction. So there's a kind of counteracting effect. But this means it gives some uncertainty in the cone resistance value. Issue number 3, I'll be quick about this one, but it's something that often happens, especially in testing soft clays, is that when you finish the test and you push the cone to the next level, the inner rod doesn't come up, it stays down. As that happens, it means that the cone has remained extended. In other words, it can't collapse itself. And it's doing that because cone resistance is quite low, and maybe some soil has got inside the mechanism and jammed it open. Now, this should not really happen in a well-prepared cone, but it can do. If it happens 2 or 3 times running, then the best thing to do is to stop the test and bring up the cone and examine it, check it, maybe replace it, and repeat the test. If you're also getting this situation, you cannot use the readings from that part of the test because they are meaningless. So be aware of that, because sometimes the operator will say, oh, the inner rods are falling under their own weight. That can't happen in a marine clay. If the cone is working properly, that won't happen. Issue number 4, again, I'll be quite quick about this one. When you store the cones between usage, it's best to cover them in grease and make sure they don't get rusty and so on before you put them away, having cleaned them and so forth. But when you test, you shouldn't have them covered in grease. When you test, you should get the grease off with some kind of solvent, and then you should lubricate them with water. I mention that because often people lubricate them with oil or grease. If you do that during testing, then soil tends to stick to different parts of it, and that tends to encourage the cone to get jammed. So using water is best. Also, you should check the dimensions of the cone. They are standard, and if the diameter and so forth becomes too small, and there are documents where you can find that tell you what the limit should be, then you should be replacing that particular instrument. So here's a very nice trace of 3 traces from 5 mechanical CPTs in the Singapore marine clay, the upper marine clay. So that's the Holocene clay. And there are, inside each envelope, there are 5 individual traces, but I've just shown the outer edges. So you can see repeatability is quite good. A couple of things to mention in this. First of all, you'll notice that each trace is roughly increasing uniformly with depth like that. It's a gentle increase, which is what you'd expect in the marine clays. Because they're close to normally consolidated, those lines will tend to come back to somewhere near or just above the 0 depth. Is what you'd expect. Also, please note the plotted scales. I've plotted cone resistance from 0 to 1 megapascal, so you can see very clearly what is going on. And I'd recommend you should always do that. So if you're receiving reports which look like the next slide, which is the same data plotted on what I call the traditional scales of cone resistance 0 to 30 megapascals, local friction 0 to 1 megapascal, then you don't see anything at all. You see very little. But in this day and age, these things are all in computer programs, and you can change those scales. So if you get data like this and your interest is the marine clay, ask the the person doing the testing and reporting it to replot them at scales where you can see in detail what is going on in those soft deposits. I've now added the weight of the inner rods. You can see it there. So you can see how the weight of the inner rod, the green line, is quite high compared to the values which have been measured from the load cell at the top. So it is quite significant in the mechanical CPT. And if I add the overburden pressure, then the overburden pressure is remarkably similar. Now, this is a good thing because they almost cancel each other out. And this is one of the slightly happy things about the mechanical CPT, because when we interpret, we normally subtract the overburden pressure from the cone resistance. So what this means is that in a mechanical CPT, approximately you don't need to do that when you interpret. You need to look carefully at these kinds of things, but that is one thing to be aware of in mechanical CPT. I've now added these dark blue traces, which are from electric CPT at the same site. I was very lucky to be able to do a lot of testing very close together to look at these sorts of things. Now, what do we see? In the cone resistance plot, it is similar, maybe slightly higher, but the local friction is much lower. And that's what we normally see. Local friction from the electric or piezo cone, much lower than mechanical, which of course means that when you calculate the friction ratio over on the right-hand side, that's also much lower. So you need to be aware of this. You do get different results from the mechanical and electric CPT, especially the local friction. So when you use charts like this, this is the famous Schmertmann identification chart. And please realize this is a guide only. It's a guide to soil type. It is not perfect. It's a guide. But it involves a friction ratio. And that means that, in fact, this particular chart is developed around the mechanical CPT. When you go to the electric CPT or piezo cone, then you will find different published charts, especially, for example, in the guide from Peter Robertson. I'd also mention from my experience of doing similar testing in stiff clays, where I've compared electric and mechanical CPT side by side, the differences in stiff clays are much bigger. So be very careful if you're using these kinds of approaches in stiff clays. And I also sometimes see people using Robertson's so-called SBT, that's soil behavior type index, which you can do in a very nice little computer program. And that's being applied to mechanical CPT results. All I have to say is be careful, it may not be reliable. It's not intended for mechanical CPT. Moving on further, I've now added vein test results to these plots. And the convenient thing about the vein test is that its values are such that you can add it to the local friction diagram directly. So the local friction diagram now also includes the vein shear strength. And you can see there how the remolded values are very similar to the local friction from the electric CPT, whereas the peak values are very similar to the friction from the mechanical CPT. And that's something I've seen a lot in the Holocene marine clays. It's pretty regular. It happens like that. Something to be aware of. So we can actually take advantage of that. So if we look at this diagram I showed you some time ago, we have reading 1, which is QC plus errors, and we have reading 2, which is QC plus FS plus errors. And to get the local friction, we subtract one from the other, which means that the errors essentially cancel out. And that means that the local friction is actually almost error-free, which is great. Therefore, why not try correlating the local friction to the vein shear strength? And that's exactly what I've done there. In this case, the vein shear strength directly from the vein test. And you can see the correlation is pretty good. The line down the middle of that diagram, you see it's local friction versus vein shear strength on the axes of the same values. And the inclined line in the middle is when the correlation coefficient is 1. It's pretty good. But at the moment, I'm using the SUV direct. So if I correct it using Bierham's factor, you'll see it gets even closer to 1. So it's a remarkably good indicator. And in fact, when I'm looking at mechanical CPT CPT and I'm wanting to know something about undrained shear strength, I quickly check that. It's definitely worth it. But such correlations really should be verified for typical deposits and sites. Don't just rely on this one diagram. Verification always important. But I think, to be honest, with the mechanical CPT, the local friction may be more reliable than the cone resistance when you want to correlate to undrained shear strength. I've now just changed the diagram. So on the local friction plot, I've added now the vane test, which is the peak value. You can see it there. And it's very close to the local friction plot. Now we're looking at another mechanical CPT. It's also 20 meters deep. It's also going through the Holocene marine clay. And it's kind of disappointing because we see this plot and we say, oh, blimey, it's almost all one value down to about 13 meters. And then it goes up in big steps. What's going on? Well, what's going on here is that it's the same basic equipment, except the load cell is not very sensitive. So what's happening there is that when the operator advances the cone, reading R1 is just one division off 0. So the needle hardly moves. So he just records the next division. And probably when he gets the second reading, it flips slightly to the second division on his. So this is the point that he's using an insensitive load cell. And that's why you get these sorts of steps. The friction ratio values are about right, and so is everything else, but you could not depend on these values to interpret undrained shear strength if you wanted to. At least I wouldn't. So the way you get around this normally is by having two sets of load cell. Each load cell has two pressure gauges, a high and a low. And what you would normally do is you start off with the light or medium load cell, the smaller one, within the Holocene marine clay. And then when you hit the deeper stiff deposits, you'd switch over to the other one. I'd have to say I don't think that's being done very often here in Indonesia, because I tend to see the kind of plot I've just been showing to you. Now let's jump to the piezo cone. We'll leave mechanical CPT behind now and talk about piezo cone. And here's a very beautiful piezo cone profile in north of Malaysia. The same profiles as before. Depth is the vertical axis, and then we have the three familiar values of local friction, cone resistance, and friction ratio. But we also have now the water pressure plot, which is coming from the pore pressure element. And I've also included on those two other lines. On the cone resistance, we have a dotted line, which is the overburden pressure, total overburden, that is. And on the water pressure plot, I've got the hydrostatic line, based, of course, on the location of the water table. So that's a typical result. It goes right through. It's the same location as those vane tests I showed you earlier on. We've got the upper marine clay, the intermediate layer, and down at the bottom, the lower marine clay. Very beautiful plot. Now, one thing you need to be aware of with cone testing is that as the cone advances into the ground, there is a part of the back of the cone, the shoulder, where water pressure is pushing on the back of the cone. And with the piezo cone, we can correct for this. And rather than using QC, we can correct it by adding on the effect of this additional water pressure to get what's called QT. So we simply use the measured pore and we multiply it by the area ratio. That's the exposed annular area where we have the piezo cone element compared to the total area of them. Typically that is around about 0.5 for most cones. It's something in that order. This AR value, you could do it by measuring, but it's best to do it in a calibration chamber. So it affects the results. So if we go back to this plot, all I've done now on the cone resistance plot, I've added that light blue trace, which is QT. And normally, if we're going to do any correlations, we're going to do it from the QT plot. Now, what are the problems for piezo cone? Well, I'd say there are quite a few, in fact, but you're dealing with very sophisticated equipment being used maybe out on a hot site where it can rain and get strong sunshine, lots of things. But I'm going to concentrate on two things today. Saturation of the filter, number one. So I've taken a particular CPT there, it's a piezo cone plot, And I've just shown the water pressure plot, and you can see there a relatively smooth trace. And if you look very carefully, you'll see little steps in it. And in fact, those steps are occurring at 1 meter intervals. And that's because they're being affected by the points where the test is stopped for a minute, and they screw on the next rod, and then they continue again. So that's the reason why you get those steps. When you see a test like that, you should reject it. Well, certainly if you want to know what the water pressure profile is, because it's wrong. So this one was repeated very close by, and this was a representative pore pressure plot, although even in this one, in the top little bit there is a sign of that step going on there. You can see it there, but generally that is a pretty good trace from the pore water pressure. So what's going on here is something like this, that we have the cone tip, and it's got in there a void which is filled maybe with oil or water or something, it doesn't really matter, but that conducts the water pressure to the sensor which measures it. Now, if you have an air bubble somewhere in that system, like I've drawn there, the white thing, then when you get water pressure applied on the outside, then it's going to compress that air bubble. Now, if it's going to compress the air bubble, that means that some water has to flow into the element. And of course, if you're in a marine clay, which is very, very low permeability, it could be very, very slow for that water to flow into the element. And that's why you tend to see the steps in a trace with a poorly saturated cone, because it's kind of catching up. The water pressure being measured has got to catch up with the water pressure on the outside. So basically, if you see that kind of trace, then you really should reject the test, or sometimes you're in situations where it's impossible to avoid it. If you push a cone through 6 meters of a partially saturated fill, then that might upset the saturation of the system as well. And then you might have to do something like using a pre-bored hole, but that would be up to you to decide how to handle the situation. So here's yet another trace on the right-hand side now. That particular one there is pretty good, but you can also see at the top 4 meters, there are also signs of that smooth trace. If you see a very smooth trace, that's normally an indication of poor saturation, especially with the steps. But below about 4 meters, it's perfectly okay. So that is to do with the importance. Saturation, to poor saturation of the filter system is the main reason for inaccurate pore pressure profiles. The second one is temperature effects. Now, there again is a nice cone resistance trace in this case, carried out on a site in Malaysia. And in this particular case, it was for a trial embankment. So we did many pizza cone tests on one site. And we were seeing this going on. Almost identical traces, but there was a parallel shift. And this was explained when we looked at the temperature results, because this particular cone also had a temperature sensor. The temperature plots, what you'll see is, in the case of the brown plot, in fact, these were done on purpose. We made it a bit too cold, and you can see how the cone heats up, and therefore that slightly changes its dimensions, and we get a slightly different result. And in the green case, it was prepared a little bit too hot, and then the temperature reduces, and we get a high trace. So the reason for the parallel shifts in this case, so we can check it. Now, I'd recommend you always do that if you're doing tests and you're testing marine clays with the piezo cone. It's well worth doing. So it only takes a few hours, but get a container, put some insulation around it, some ice into it, fill it with water, and allow it to melt. Once it's done that, place a thermometer and your cone into the water, and then you remove the insulation and you monitor temperature versus the 0 reading for the cone. Well worth doing if you're doing a serious investigation of the marine clay. And here's one of the results we got, actually quite bad. You can see there the QC reading versus temperature on cone number 315. And there are some more for different cones. They were quite different, some of them. 313, not too wonderful. And 315 and 317, we decided were not usable, and we sent them back to the supplier. In fact, what the supplier did, he did some work to improve the temperature stability, which can be done. And when they came back, they were far, far better. Now, in fact, I would recommend that you always do this before testing marine clays with a CPT, just to be sure, because you'll be told these days, oh no, cones are all properly temperature compensated, there won't be any effect. But for a few hours like this, before a big investigation, it's worth checking. And in fact, you could even include that as part of your specification. And then when it comes to carrying out the test, I think it's really important that you should carry out a simple temperature stabilization of the cone first. So using the same equipment, put the cone into the water at about 28 centigrade. In Indonesia, Malaysia was the same. It'd be about right. And leave it there until you get a nice stable zero reading, and then carry out your test. You can write that into your specification as well. Now, what I've just been showing you was from work done more than 30 years ago. So maybe equipment is much better now. Well, it probably is. But this is some information I saw from a site in Jakarta not so long ago, 2013. But in this case, when I went to the site to watch what was going on, there was no temperature conditioning. There's no temperature sensor in the cone. So the question is, you can see a parallel shift there in the cone resistance. Is that a real soil property, or is that a measurement error? And you've really got to think about it. In fact, in this case, the site is up in the north of Jakarta here. It's a container terminal. The piezo cone tests were about 100 meters from each other. That could be responsible for some of that shift if there were differences in the fill thickness above, but it seemed to be unlikely there was any big difference. The indication there is probably a temperature effect. So I thought it would be quite useful to have a quick way to look at these profiles and decide quickly on the degree of consolidation. Is it normally consolidated or over consolidated or under consolidated, in other words? And to do this, we're going to make use of a very famous little relationship which comes from Professor Mesri and we're going to combine that with the cone factor, which we're going to come to in a bit more detail in a second. That's the Mesri relationship, which says that the ratio of undrained shear strength to pre-consolidation pressure is around about 0.22, which works for a wide range of alluvial clays. So if a clay is normally consolidated, then PC dashed, pre-consolidation pressure, is the same as the current vertical effective stress. So I can switch that in the equation as you see there. And I can then combine that with what we call the cone factor equation, which I'll come to after these slides. And in doing that, I get this relationship where I get a combination of the two, which says it gives this relationship for any soil which is normally consolidated. So if I use an NKT value of 19, which is about right for these clays, I get this expected cone resistance. And if I put in some typical values for the marine clay, I find that QZ, that's the thickness in meters, in megapascals. So this means that it's about 0.2 megapascals at 5 meters, and add that to foresee that this is suggesting that the blue trace is actually under consolidated, which is unlikely to be the case. The brown one almost exactly normally consolidated, which is also surprising, and the green one quite well over consolidated. Because conclusion was that shift is principally due to cone temperature during preparation. I also applied this idea to the previous data we looked at, and you can see how it shows that the blue trace just slightly over-consolidated, which is what we expect in that deposit. Please be aware that this check is done against QT, not the measured QC. One little related problem is this one. What you see there is another one of these beautiful Delft samples. But what's happening here, it goes through about, and then below it is the marine clay. So when you look at the trace of cone resistance, you have very, very high values down to 10 meters, and then it drops down to the low values of the marine clay. Now, the problem is, if you push a cone through 10 meters of sand, dense sand like that, it gets hot. So the problem is, if a cone gets hot, will that affect this or create some zero shift? Well, we don't really know. But the problem is, you have to ask then, is the QC profile below actually representative? Temperature sensor would help. How can you solve this problem? Well, it's difficult. Either you can get through into the soft clay and wait for quite a long time and observe the cone resistance, or you can pre-bore and avoid pushing the cone through the sand. Right, so I've just reached 1 hour and I've got a little way to go, so I shall keep, I want to get through this. We've got a little more to go, but hopefully you'll find it worthwhile. So back to our very nice profile, because I want to talk a bit about correlation now, a few pointers about correlation, principally to obtain undrained shear strength. So what I've done now with that same plot, I've added the vein test data to the local friction plot, both peak and remolded. You can see again how the local friction is very close to the remolded vein shear strength, as we saw the Singapore marine clay. I said I've seen that in many cases or tests profiles in Malaysia and Singapore. So I can take the data and do a correlation. This correlation is plotting QT minus sigma V against the vein shear strength, and you see the results I get there for both the upper and lower marine clay. By doing using logarithmic axes, then similar values of NKT are simply parallel lines. So it's quite a nice way to look at the spread of data. And therefore we interpret NKT from that expression, and you can see the values there. I don't need to read them to you. You can see what they are coming out for the upper and lower marine clays. And that's based on the vein test. So I can plot these against plasticity index, because PI is often a useful indicator of, or helps you to interpret these things. And in this case, the PI is all then added the lower marine clay, which is generally lower PI. And you can see the values are a bit higher. And I've also added there, that big dot is actually glacial till from the UK, but it follows a similar trend. What you'll notice is that curve. So if I then correct the value of NKT by correcting SU using Beerham's factor, I find that the cone resistance factor, the NKT, is remarkably uniform now against PI, almost independent. And typically for the UMC upper marine clay, about 18 or 19. And that's why I used 19 earlier on in that little exercise I did. Before I leave this topic, just a couple of warnings about cone factors. You will often see papers of published values of cone factor, and please be aware of what's going on. Now, if I write this expression very simply as undrained shear strength equals cone resistance of some sort divided by a factor, a cone factor, then you've got to understand what's being measured. So when you look at that, first of all, what type of cone, mechanical or electric or CPTU, is the undrained shear strength an actual value, maybe from laboratory testing, or is it a vein test result? If it is a vein test result, was it corrected? Sometimes you're not told. is the cone resistance QC or QT? But of course, you can only get QT from the piezo cone. And has the Q value been adjusted for the total overburden pressure? Unfortunately, it's often not clear. So for example, you could have all of those different expressions being used. And the one I used just now is the last of those values of the cone factor, depending on how you carried out the correlation. Important to be aware of it. We can also correlate the results of piezo cone tests with the overconsolidation ratio. Now, this is really the topic for the next webinar. So I'm going to actually, because I'm a little bit over 1 hour already, and I've got a couple more topics to look at briefly, let me hurry past this because there are techniques for doing this. I'm going to look at this in much more detail in the next webinar. So there is this AQ parameter, which is basically normalized cone resistance, which we can correlate to find out the overconsolidation ratio. And also we have the BQ parameter, which is a water pressure ratio. That can also be used and help us next webinar. So 2 last things to look at. They're both very practical. I just want to look at this particular case study, which is a trial embankment built in Malaysia. And this also is going to be the subject of the next webinar in much more detail. But I just want to look at one thing, which was stability. So this was a very detailed trial embankment built some time ago. Control embankment, an embankment with vertical drains, and a high quality site investigation. Much more about this in the next webinar, as I mentioned, but just look at one thing. There's a nice cross section showing all the instrumentation, dimensions, and so on. Let's not worry about that too much, but just look at one point. We carried out lots of very high quality sampling. We got, there are some profiles of Atterberg limits, undrained shear strength, pre-consolidation pressure, and compressibility. More about that next month. And here are the plots from a typical piezo cone test. But I just want to take one thing. There is my plot of the check on, is it normally consolidated? It's exactly what you expect in this kind of deposit. So we take this kind of data to determine the cone factor, plotting again the cone resistance minus the overburden pressure against the vane shear strength. And from this, we get an NKT of 13.1. So I can use that then to calculate a profile of undrained shear strength from that particular trace. But what about temperature effects? Say we also have this problem of this parallel shift, and I use those 3 profiles of undrained shear strength. So now I have 3 profiles of undrained shear strength, and they are significantly different. And then maybe we need to remember about Bierham's correction factor. And of course, that reduces the undrained shear strength, and I get 3 more profiles. So what I'll then do with my 6 profiles of undrained shear strength, I'll carry out a simple check of the stability of the embankment. And here, which is in a slope stability program, in this particular case, we get a safety factor of 1.009, which was for the middle temperature and the corrected undrained shear strength. If I now tabulate all the results from the 6 different cases, you can see the values here. So if we do not correct or we have the wrong temperature, you can see a potential huge variation in the safety factor. So the value, but the extreme values are all the way from 0.65 all the way up to 1.8 in the safety factor, due to either misinterpretation or a poorly conducted test. So that's why you need to get this right. This is information about settlement behavior. That's going to be coming in the next webinar. So the very last thing I want to talk about, it's going to take me a couple of minutes, is planning site investigations using the CPT, because I think this is quite often done badly. So there are two main approaches that I come across. This is assuming, of course, that the main aim is the site investigation of soft soils. Approach one is like this. We'll do boreholes and we'll fill in with CPTs. I'd say this is slow and inefficient use of in situ test methods, and it does not provide adequate correlations to help you check how to interpret the parameters. Approach two is like this. We'll use CPTs and develop very quickly a detailed profile of the soil conditions. And then based on this, we'll plan a relatively small number, but very detailed profiles of vein tests, also sampling and laboratory tests. And that's what I want to show you very quickly in a case study. However, I'm suspecting that approach one is probably the most common. Here is the site, back to that nice site with the friendly water buffalo. This is actually up in the north of Malaysia, north of Penang. And the original site investigation consisted of 7 boreholes over about a 1.5 kilometer stretch of the North-South Expressway. And decision was from the original boreholes that there's some soft soils near the ground surface, and they decided they were going to build a 440-meter long continuous viaduct to get across the road and the irrigation from some boreholes. So what can we do then to improve this? So the client decided to carry out additional site investigation. In fact, we did 34 pizza cone tests to get a nice profile. And then from that, we planned 8 boreholes and 13 vein tests. But we only did that after we completed the pizza cone tests. Here is a typical pizza cone test. It's a very beautiful profile. By now, you're kind of familiar with the layout and what we see here. And there is that particular test plotted on the profile. Test D4A, where we identify an upper clay, which is the upper marine clay, in fact, and a lower clay, which is the lower marine clay. And there's some sand layers as well. So not a desperately different embankments. There are the rest of the pizza cone tests added to that profile, identifying those layers again. And then, of course, we can draw some lines to see where those main layers are. So we now have a very clear idea of the arrangement of those layers. Having done that, we plan some boreholes and some vein test locations. And then from that, we derive information. And for the 2 layers, the upper clay and the lower clay, we get some very nice profiles of Atterberg limits, undrained shear strength, pre-consolidation pressure, and compressibility. And based on this, the result was that the viaduct was changed to 3 short span bridges with embankments. The SI cost about $100,000 in those days. It costs quite a bit more now. And it saved about $2 million in construction costs. So I did go over my hour, as I thought I probably would, but I hope you don't mind. So just some summarizing comments. CPT data from the Holocene marine clays of Southeast Asia, is it suitable to predict engineering properties? I'd say definitely yes, but we have to be careful. Good equipment, good procedures, suitable load cells, those all make the mechanical CPT suitable to do this, but always being aware of the limitations. Certainly, I think you should give consideration to interpreting the undrained shear strength from the local friction. It seems to work really well. Unfortunately, one thing you can't check is inclination. So you have to try and solve that problem by good setting up of the test, and as I mentioned earlier on. When we move to the pizza cone, then that really offers a whole magnitude of order of magnitude of improvement. In other words, 10 times better. But things like pore saturation are fairly obvious, and we can minimize that by good procedures. Temperature effects, as I mentioned earlier on, I believe still, even today, you should check it. Why not? It doesn't take long, and it just helps you make sure you've got good, consistent results. I mean, sometimes one way to approach this, if you're doing a major site investigation in the marine clay and the equipment comes on site, do 3 tests close together in one corner of your site and just see how those profiles compare to each other. One simple way of getting an idea. It might cost you a little bit, but just helps you understand the consistency of the testing. If you're using cone factors to interpret, please be careful to understand exactly how the cone factor has been defined, as I mentioned earlier on. And that little embankment case study also shows the importance of good procedures and correct method of interpretation to make sure your safety factor is about right. I forgot to mention, in that particular trial embankment, that embankment was very close to failure. In fact, we had to unload it to prevent failure taking place. So its safety factor was close to 1. So I forgot to mention that at the time. But of course, for soft soils, you really need to use the CPTU so you can get the corrected cone resistance. So CPTU should be the standard for these Holocene marine clays. And in the 6th webinar, we're going to look in much more detail at the issue of settlement, in particular, the effect of this testing on the estimation of the pre-consolidation pressure. And that'll be in July. So, I'm just going to mention one other thing. We have this completely different topic for a second. On the 7th of July, I'm presenting yet another webinar. Sorry, it's me again, but on a completely different topic, which will be a piece of software for design of reinforced soil retaining walls called Tensar Soil, and we're going to look at the use of what's called the 2-part wedge method of calculation for internal stability. So I think that's where I come to a finish. Thank you very much for going slightly over the hour, but I will try to deal with any questions if they come up. So